Hello, in the previous video we studied different properties of matrix operations. We were talking about inverse of a matrix in general idea. Like if you compare the system of linear equations ax equal to b, right, with the ax equal to b. We know that if a is not 0, then the x is equal to b over a. But actually that is what? That is a to negative 1 times b, right? So we multiply b with the inverse of a. We get unique solution of this equation. So if you have a system of linear equation ax equal to b, when can we solve this system using the inverse like this? Okay, so that is the main topic in this video. Let's consider the following definition. Suppose that you have some square matrix A of the size n by n. A matrix B is called an inverse of A if AB equal to BA, and that is identity. So we know that identity matrix plays the role as 1, right? As 1 in scalar multiplication. And if you have A times B from the left and A times B times A from the right, and you have the same identity, so in this case B is an inverse of A, and B is denoted by A to negative 1. Okay, or I can write this identity as A times A to negative 1 equal to A to negative 1 times A equal to identity In. So that is the definition of an inverse of this matrix. And in this case, if a matrix A has an inverse, then A is called invertible, right? In this case, A is called invertible. Okay, invertible. So this is a very important class of matrices. Very important. Okay, so now you might think about the system of linear equations. You might think about the system of linear equation. We go back to the system of linear equation. We have ax equal to b, and we suppose that a is square, okay, and not only square, a is invertible. Agree? So if a is invertible, I can multiply, both sides of this equation by a to negative 1, but from the left. I have to multiply from the left. Okay, so I have a to negative 1 ax equal to a to negative 1b. Don't forget that matrix multiplication is not commutative. So this is different to b a to negative 1. Agree? And since a to negative 1a equal to identity, right? So you have a I n equal to x equal to a to negative 1b. And since I n is 1, right, in matrix multiplication, that is just x equal to a to negative 1b. So this logic gives you some way to solve the system of linear equation using the inverse matrix. Using the inverse matrix, okay? That is the unique solution of the original system. All right, so how do you think if a matrix A has inverse? So is the inverse unique? Yeah, it should be. Okay, so if A negative 1 exists, then it is unique. Okay, so there's no way to have two inverse for a square matrix. Agree? Let's consider some examples. First example show that the following matrices are inverse of each other. Following matrices are inverse of each other. Okay, so I have matrix A equal to -1, 2, -1, and 1. And B is 1, -2, 1, -1. So I need to show that AB equal to BA and equal to I2, right? The identity matrix of out of 2. Let's say, what is AB? That is -1, 2, -1, 1 times 1, -2, 1, -1. So that is AB. Okay. Let's do multiplication. I take the first row, multiply with the first column. I have -1 with 2 is 1. And then the first row, if you want, you can, take the first row, multiply with the second column, right? And you get -2 with 2 is 0, right? Similarly, you take the second row with the first column and second row with the second column, you get 0 in here, and here you have 1. So that is the identity, right? And you can check that, BA is 1, -2, 1, -1 times -1, 2, -1, and 1. And I bet you get exactly 1, 0, 0, 1. So that means A and B are inverse of each other. Does it make sense? Second example, we need to find the inverse. Let's find the inverse. Of the following matrix A equal to 1, 4, -1, -3, if as x. All right, so we can do using definition. We can solve this problem using definition. Like, okay, suppose that B is the inverse of A, right? Let's say that is A, B, C, D. And we need to find B. We need to find A, B, C, and D such that, let's try such that AB equal to BA equal to identity. So if this system has solution, we are good. We can find B. Otherwise, A is not invertible. Okay? So don't forget. We need to find the inverse of A if the inverse is X. All right. Let's solve this. Let's find AB and BA. I have AB equal to 1, 4, -1, -3. And here A, B, C, D. Okay, so this is what? This is A plus 4C, is B plus 4D, and then -A minus 3C, and then -B minus 3D. This is 1, 0, 0, and 1. Okay, and then you have a system of linear equations. Because you compare two matrices, right? You compare two matrices. This one with the 1, this one with 0, this with the 0, and then this guy with the 1. So you have the following system: A plus 4C equal to 1, B plus 4D equal to 0, -A minus 3C equal to 0, and -B minus 3D equal to 1. So if you can solve this, then we can get A and B and C and D. A, B, C, D. Okay. So let's look at these 4 equations carefully, and I see that actually, the first with the with the third one, this is 2 equations in 2 variables, A and C. So basically we can solve these two equations, right, to find A and C. and then the second one with the fourth one. So it looks pretty easy, right? So let's pick the first and the third. I can add, right? I add the first and the third. I have C equal to 1. And from here, I can plug this into one of them, like let's say the first one, right? So I have A plus 4 times 1 equal to 1. And so A equal to -3. Similarly, I can add two equations, the second and the fourth. I get D equal to 1, right? And I plug D into one of them, like let's say the second one. So B equal to -4D, that is -4. I already have A, B, C, D. So the matrix B is what? Is -3. AB is -4. C is 1. D is 1. Okay. So we just put AB equal to identity, right? So let's check that BA is also identity. Need to check. Let's check that BA is also identity. Okay. And we are done, right? So I have -3, -4, 1 and 1 in here, multiply with the A. A is 1, 4, -1, -3, right? And let's pick the first row times the first column. -3 with 4 is 1, and then -3, 4, I get 0 in here. Yeah, that is identity. So this is the inverse of A. A to -1. All right. Now look at this system again, right? You have this product equal to this matrix. Okay. So basically, what we are doing here, right? We are solving two systems at the same time. Is it correct? So, because when you multiply the matrix A, right, with the first column, that will be the first column in the identity matrix. You see that? So if I do separately, I have two systems. 1, 4, -1, -3. Okay, multiply with AC equal to 1, 0. And the second one is 1, 4, -1, -3 times BD equal to 0, 1. Is that correct? So basically, we have two systems, right? Two systems. And, finding an inverse of this matrix A is nothing but just solving these two systems. So if I write these two systems in a compact form, I have the following one. I have 1, 4, -1, -3. That is the first, right? The first one is 1, 0, right? And the second one is 0, 1. You see, if I write in the compact form, I have two systems like this. We learn how to solve, system linear equations using Gauss elimination and Gauss-Jordan elimination in the first chapter, right? So basically, in order to solve this system, you can do all operations at the same time. So we can solve two systems at the same time. Is that correct? All right, so let's do that again, right? And then we'll see the method how to find the inverse of a matrix if x. Okay, so if I solve these two systems, so that means I have to make a reduced row echelon form of the coefficient matrix. This is coefficient, right? So let's make a reduced row echelon form. From here, I fix 1, so I add the first row to the second, right? I write in here the first row to the second. I get 1, 4, and then 1, 0 in here. I get 0 in here. So 4 with negative 3 is 1. 1 with 0 is 1. 0 with 1 is 1. Okay? And then what we have in here, I have 1, right? I already have the row echelon form. Now I need a reduced row echelon form. So I multiply the second row with negative 4, add to the first. The second row with negative 4, okay, add to the first row, okay. So I have 1 in here, 0, 0, 1. Agree? So 1, 1. And then this is with negative 4, add to the first, so I get negative 3. This guy, negative 4, add to the first, I got negative 4. You see? And we already have reduced row echelon form in here, you see? And all these columns in here should be the solution of two systems, right? The first column is the solution of the first system, and the second column is the solution of the second system. You see? And that's what you have in here. This is your matrix B. You see that? And that is the inverse of A. Right? So from this example, it tells you, in order to find the inverse of a matrix, you just need to write the original matrix, right, in here, and the identity matrix all together in this form. So you can write A, and then here is identity, let's say IN in general, and then you can use row elementary operation to get a reduced row echelon form. I write here to get the reduced row echelon form. And then if A has an inverse, so the reduced row echelon form should have the following form. Means in here you should have identity. And in what you have in here, that should be A to negative 1, the inverse of A. Okay, so that is the general method how to find the inverse of a matrix if A exists. All right, let's consider another example. Okay, I can write example right here. Okay, we have matrix A is 1, negative 1, 0, 1, 0, negative 1, negative 6, 2, and 3. Let's find the inverse of A if A exists. Okay. So according to the method we have seen, we need to write the following 1, 0, 1, 0, negative 1, negative 6, 2, and 3. In here I have 1, 0, 0, 0, 1, 0, 0, 0, 1. I wrote like this because I want you to memorize that actually we are solving 3 systems at the same time in this case. The first system is corresponding to the first row in the identity matrix. The second system is this, and then the third system is this. So the solution of these 3 systems will form the inverse of A if A exists. Agree? So I need to use row elementary operations to, okay, I fixed 1 in here, so I need to make these guys become 0. It's pretty easy. For the second row, I can multiply the first row with the negative 1, right, and add to the second row. Okay, so I have the following: 1, negative 1, 0. That's what we have. 1, 0, 0. This is the 0, and then negative 1 with negative 1 is 1, plus 0 is 1, 0, so I still have negative 1 in here. For this one, I will get negative 1 in here. I have 1 in here, and here is 0. You see, when you multiply, the first row with negative 1, you have to multiply all entries, right, on the first row with negative 1, and you add to the second. Don't forget that. Okay, you don't want to do with only one entry. You need to do with all entries in here. Okay, all right. Now with the second one, with the third one, I just multiply the the first row with the 6 and then add to the third, right? I have 0 in here. Negative 1 with 6 is negative 6 plus 2 is negative 4. I have 3 in here. And then 6 in here, a 0 and 1. So I finished with this leading element. Now I move to the second one, right? I move to the second one, which is right here. Then you can see actually we need to multiply the second row by 4 and add to the third, right? And add to the third. So I have 1, negative 1. You can do, okay, let me erase this. Let's do that all together, okay? So I fix the second row, okay? I keep the second row in here, 0, 1, negative 1. In here, negative 1, 1 and 0, okay? And then I have 0, 0 in here. 4, I have negative 4 with 3 is negative 1. And then this guy with negative 4, with 4 is negative 4 plus 6 is 2. This guy with 4 is 4, 0 with 4 is 0, and 1 in here. Okay, now I have this guy become 0 already, right? We still have this guy. I just add the second to the first. Okay, let's do that all together, okay? So I write in here, I add the second to the first, okay? I have 1, I have 0, I have negative 1, okay? I have 0, I have 1, and I have 0 in here. Agree? And then we already have the row echelon form, right? But here we have negative 1. I will multiply the third side by negative 1 so that, I will have plus in here, negative, negative, and negative in here, okay? So I just skip that step. And now we have 1 already in here, which is good. Now I will multiply the third row with the 1, add to the second, and add to the first. And then all these two terms will be 0. All right, so I can write in here R3 times 1 add to the first, R3 times 1 add to the second, right? Then we have 0, 0, 1 in here. I have negative 2, negative 4, negative 1. And then here I have 0, 1, 0. I have negative 3, and negative 1. You see? And then the first row looks like 1, 0, 0. And then I have negative 2, negative 3, and negative 1. So we already have the reduced row echelon form, and that is the identity matrix, which is good. I have 3. And this is what? This is the inverse of A. Okay? So we have A to negative 1 equal to negative 2, negative 3, negative 1, negative 3, negative 3, negative 1, negative 2, negative 4, negative 1. You see, actually in this method, right, if the matrix A is not invertible, means the matrix A does not have any inverse, then the reduced row echelon form should not have this form. Don't forget that. Should not have this form. You see another form right away, you will not have identity over there. And at least you will get, 1, 0 rows. I mean, if A does not have any inverse. Don't forget that. Okay? So, this method is very general, and that helps you to find inverse of any matrix, and even that helps you to check if a matrix has inverse or not. Of course, that is a long way because we need to do, all operations in here. We need to use row elementary operations to get the reduced row echelon form. Okay? In the next chapter, we will learn another method how to determine if a square matrix has an inverse or not. But right now, that is the only way we know. Okay? Right, so in order to finish this video, I would like to show you how to find inverse of 2 by 2 matrix. And for 2 by 2, there is a pretty beautiful formula. Suppose that you have a matrix A as A, B, C, D, 2 by 2, and AD minus BC is not 0. Then, in this case, A is invertible, and the inverse can be found as 1 over AD minus BC, means the product of entries on the main diagonal subtract by the product of other entries. And in the matrix, you just need to interchange A and D, right? So you interchange A and D, you have D and A right here. With the B and C, you just add negative B and negative C. That's how we can find the inverse of 2 by 2 matrices if Sx. Okay, so it's pretty easy. You just multiply this guy with this guy, and you can check, right? You can check if the product is identity or not. So I will leave that to you as a simple exercise. I just want to do a couple of examples, and I tell you again, right? Each time when you have 2 by 2 matrices, please use this formula, because that saves a lot of time from you. Okay, let's consider the following example. I have A equal to 3, -1, -2, and 2, and B is 3, -1, -6, and 2. So the question is, which matrix is invertible, right? So if you consider matrix A, what is AD minus BC? AD minus BC is 3 times 2 minus -1 times -2, which is 6 minus 2 is 4. This is not 0. So the matrix A is invertible. You see? And in this case, A inverse is what? Okay, 1 over 4. You see? We already have 4 right here, right? AD minus BC. And then inside of the matrix we have, I interchange the position of D and A. I have 2 and 3 in here. -1, -2, they are there, but with the negative sign, so I have 1 and 2. Or I can write that is 1/2, 1/4, 1/2, and 3/4. Okay, so how about B? For B, you have AD minus BC equal to 3 times 2 minus -1 times -6, which is 0. The matrix is not invertible. Not invertible. Right? Okay, look at this. Look at the matrix B, right? So you have 3 times 2 minus -6 times -1 is 0. That means 3 times 2 equal to -6 times -1, right? Okay, I just want to show you one thing, right? And then you divide 3 by -6 in here. That is equal to -1 over 2. What can you see from this identity? You have 3 -1. 3 -1, that is the first row. -6 and 2, that is the second row. This identity tells you that 2 rows in B are proportional, right? 2 rows are proportional. You see that? So that means when 2 rows are proportional, actually, when you do matrix elementary operation, 1 row should disappear. So that's why in the row echelon form, you have at least 1 0 rows. Right? We have at least 1 0 rows. So that's why, the matrix is not invertible. Not invertible. Okay, so I think we can finish our video in here. In the next video, we'll study more properties and we finish our section. If you have any questions, please feel free to let me know. All right, thank you.